Hello, chemist. Jolly again. This time, let's talk about something called the Diels Alder. But before I do that, I need to talk about some cyclic systems. So let's jump over here. All right, not just one ring, but what if we have multiple rings? Well, there's different varieties. If they're attached at the same carbon, those are like spirocyclic. We don't see those very often, okay? But one single atom is common to both rings. The other two we're going to see quite often. All right, so fused is where these two carbons are similar to both sides. So these carbons are required to finish that ring and to finish that ring. So we just call those fused. All right, there are some that I wish I had known what their names were when I was going through, uh, well, pretty much graduate school. It took me a long time. Slow, obviously, I am. All right, so two aromatics in a row is naphthalene, three is anthracene. Now, a little bit angled is phenanthracene. This one has a five-membered ring right there. That's called fluorine. And then if you have just four stacked on top of each other, that one's called pyrene. Now, again, do you have to memorize those? No, absolutely not. But there are a lot of fused systems in the world, and a lot of them have very common names. So rather than trying to name them systematically, they are given these wonderful common names. So could you name them systematically? Yes. If you went to the nomenclature, it would show you to do basic bicyclic nomenclature, but not, horribly important unless you're doing research. All right, so we've got our fuse systems, but the ones that I really want to show you that is neat is something called the bridged system. And so a bridge system means that there is more than two carbons that are similar. So if I was going to fuse, I would put it over here on the right, left, top, bottom, but I'm going to put it right through the center there. Different color. So 1, 2, 3, 4, 5. That ring has 5. Well, guess what? So does this one. 1, 2, 3, 4, 5. Ooh, guess what? Ooh, blue. 1, 2, 3, 4, 5, and 6. There's technically three different rings sitting in there. Okay, that's called a bridged system. And it's very difficult to see unless you kind of tilt it into a three-dimensional view. So the way that you're going to draw these tilted ones, okay, go up. Okay, now notice those were just a little bit angle. Is first that, and then go straight up for your bridge. So in this case, there's only one carbon for my bridge, and it'll just take some getting used to draw those. But here is an example of a technical name and where the individual pieces talk about. But as long as you can draw them and you can recognize them, that's really the only important thing for our next reactions. All right, the Diels Alder, a concerted 1,4 cycloaddition of dienes. How is that for a mouthful? All right, concerted, all at once. Cycloaddition, you're going to make a ring. How are you going to make the ring? 1,4 addition. And what are you going to start with? You're going to start with dienes. Now, of course, you have to have two different pieces. And so your two pieces are your dienes and your dienophiles. You have to have both of those. And I'm going to jump over to the whiteboard to give you a generic. So this is the Diels Alder 1,4 cyclo. All right. Generically, you're going to start with a diene. And remember, they are more reactive in their cis. And you also have to have access to the p orbitals And if they're in the S-cis conformation, do you see right here? You can actually complete a ring. So you have to be in the S-cis position. So there's your diene. There is your nucleophile. You're going to react that with some kind of an alkene with an electron withdrawing group on it. This is called the dienophile. And what is going to happen is you're going to start with the density. It is going to attack the pi bond. Okay, now the flow of electrons is going to go towards the electron withdrawing group. And then that bond will react there, which kicks this one right there. And remember, it is concerted. So you're going to make a six-membered ring. All right, let's put some numbers. 1, 2, 3, and 4 is 1, 2, 3, and 4. A and B is A and B. So in a nutshell, you are going to combine a diene and a dienophile, and you're going to make a six-membered ring with a double bond. And that double bond is between where they started. That is called the Diels Alder. Now, is just going to happen spontaneously? Of course, sometimes, but usually it requires a boost. Okay, so it usually requires some kind of heat, and we're talking a lot of heat. We're talking a lot of heat. All right, let's try another one. What if, whoa, it's starting as a ring? Again, follow the flow of electrons. So draw your six-membered ring. Put the double bond in between where the original two were. And this is where that bridged issue comes from. Let's do red. So 1, 2, 3, 4, and 5. So 1, 2, 3, 4. And that little pucker is the 5. There's A and B. And if we wanted to draw that, there's the basic structure. There's the basic structure. And then the electron withdrawing group would be right there. Now, it does matter, the stereochemistry of the electron withdrawing group, but just for basics, we'll leave it right there. All right, let's try another one. Wow, I'm just so original. Just can't help myself. Oh, and then don't forget the heat. All right, attack. Make my nice little six-membered ring. Put my double bond in between where they originally were. Now this time there was 2 carbons there. 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. A and B. Whoops. Have to fix that. There's A, there's B. And then again, my electron withdrawing group will talk about where it's going to be located. When you draw this one at an angle, you just kind of make 2 points up there. And so generically, that's the Diels Alder. All right. So what is going to be important about my diene? What is going to be important about my dienophile? My diene must be in the S-cis conformation, and it has to be donating. Okay, it's supposed to get the ball rolling. It is the nucleophile. So if you attach something to it, that will help. That will help. And so here's some common dienes. Here's 1,3-butadiene, 1,3-cyclopentadiene, 1,3-cyclohexadiene. Those are the 2 I just used. And then you can just do variations, like this one has a methyl group on it. Okay, this one has a methyl in a different location. Just generic dienes. What kind of electron withdrawing groups are we talking about? Any kind of not withdrawing, electron donating groups. Remember, carbons are considered electron donating groups. So technically, that is called a donating group. All right, let's do that one. 1, 2, 3, 4, 5. So remember, you have to draw in the S cis conformation. All right, what do we want on here? I'm just going to put electron donating group. Okay, that'll make it more reactive. What do I want on my diene then? Now the diene, on the other hand, it needs to be attacked. So the reason the electron withdrawing group works so well is it really weakens this bond. And I find it really easy to visualize that with a carbonyl. And so if we put that there, all right, this will go up and it will make that. Aha, look at that. That is an excellent place to be attacked. And so that's why you need a withdrawing group. And it's always on the opposite side. So your electron donating group will go after the opposite side of your electron withdrawing group to make your 6-membered ring. And then here are some dienophiles. Okay, acrolein, which would be an aldehyde, and then just a methyl vinyl ketone. And then I give you some variations, specifically with some stereochemistry, because we're going to play with that. All right, what do we do with the stereochemistry? It's conserved, okay? End of statement. If you start cis, you're going to end cis. Wait a second, what cis is she talking about? This is about the alkene in the dienophile now. Trans, trans. So let's say we started with our trans. One of those would be the electron withdrawing group. All right, because they were trans, and I don't care which way you put it, but if you put that one as a wedge, you have to put that one as the dash. If it had been cis, you could either put them both wedged or both dash. So that one came from cis, and this one came from trans. So it's stereospecific. It is going to retain whatever that dienophile had. Huh, okay, not bad. Now, what if I make a bridge system? Do I have to worry about where my group is there? And the answer is, of course, yes. All right. So in that example, I had my electron withdrawing group. It could be in two locations. Okay, so I'm showing that one's up, but it is close to that bridgehead, which means there's steric hindrance. So this one is less stable. And because it's going outside up to that bridgehead, this one is called exo, where this one, green, this one is away, or if you will, tucked inside, underneath, however you want to phrase it. And that one, as long as there's not other things, hanging down there getting in the way, is called endo. And so endo is favored, which is basically just saying, use the common rules of sterics and electronics. And this one happens to be sterics. Okay, so what do we know? We know that the factors favoring the Diels Alder, we need electron withdrawing groups on the dienophile, okay? We need electron donating groups on the diene. The diene is enough, but it would be nice to give it a little extra. We need high temperatures. It's nice to have high pressures. And a little help is always nice with a Lewis acid catalyst. And I'm going to go over to the whiteboard and we're going to do just a couple more examples. All right, so your diene, I know it has to be in the S cis. I would love to have an electron donating group on it. All right, what would be that electron donating group? If you remember back to the resonance handout, we played with the different variations like the oxygens, the nitrogens, things like that. Okay. Technically, that's also getting into Lewis acid-based chemistry, so it kind of works both ways. All right, so we have our wonderful electron donating group, and let's do, let me see. Let's do that one. All right, so first of all, pick out our diene. Our dienophile. How do I know it's a dienophile? Because it's a alkene with an electron withdrawing group. So really, what is it seeing? One variation is that. Now, don't forget, carboxylic acids also do other chemistry. I'm ignoring that it's a carboxylic acid and it's just a withdrawing group right now. All right, so my donating side will attack the partial positive. Carbon can only have 4 bonds, so it's going to kick there. And do 2 colors here. 1, 2, 3. And then what color? Blue. Yeah, good thing I said that and then didn't draw it, huh? And so where is my electron donating group going to go? Okay, it'll be right here. This is not a bridge system, so there's not an endo or an exo. You could do an R and S. And then this one would be up here. And in this case, because this electron donating group, it will keep the configuration, but you could get different isomers. All right, that is generically a Diels-Alder. And I would love, some high heat, some pressure, all the help it can get. All right, that in a nutshell is the Diels-Alder. Except, yeah, you thought I was gonna, you thought I was gonna go away. Sorry, psych. The reason I went to the whiteboard is so I could do a couple of examples, and then I only did one. Okay, the other thing that I wanted to do is I wanted to draw the product and work backwards to what we had. All right, so let's say this is the system. Hey, could you pick out the pieces from the Diels-Alder? All right, find your double bond and then put the two away from it, which means that those are the sigma bonds that you are going to form, which means this is the alkene that you had to start with. All right, so the way you do that is cleave, cleave. There would be your diene, and you would put the double bond back in its place. And there would be the two pieces from that molecule. Mm. All right, so let's say we have this molecule. Whoa, can't even tell what's going on there. I'm trying to show you this one is trans to that one. It's opposite to that one. Okay, we're going to do the same thing. Go and find your double bond. Your double bond is in the middle of where the two diene bonds should have been. So it should go there and it should go there. And you have to look for your electron withdrawing group because that will be your dienophile. So that has to be there. And so 1, 2, 3, 4, 5, 6. I know I'm drawing that ugly, but that basically is what my diene look like. And that is what my dienophile look like. And I knew it was trans because these were opposite. And that's how you would do retro synthetic analysis, which is a fancy way of saying, can you actually work backwards and tell me what the starting material is? All right, now I'm done talking about the Diels-Alder. All right, until next time, jolly out.